Okay, so let's go ahead and get started. So last class, we discussed in sort of general terms the modifications that we would have to make to our Feynman diagram computational techniques for computing the observables of a quantum field theory using perturbation theory. And of course, the goal of these discussions is to write down the theory of quantum electrodynamics and to spend a little bit of time studying it using these Feynman diagram techniques. But before doing full quantum electrodynamics, what I'd like to do is consider a slightly simpler example, which is a theory not of a photon coupled to an electron and a positron, but rather a theory of a real scalar field, phi, coupled to a Dirac fermion. So this is just a slightly simpler version of quantum electrodynamics, where instead of having a photon coupled to a Dirac fermion, we have a real scalar field. This theory actually is known, it's actually a quite famous theory, and it's quite important for a variety of reasons. It's known as the Yukawa theory, and in fact, it was developed as a theory of the strong nuclear force. Where here, the fermions that we're discussing are the various nucleons, such as the protons or the neutrons that are present in the nucleus of an atom. And the bosonic field, the scalar field phi, is supposed to be the carrier of some new force, the nuclear force, that binds the nuclei together at the core of an atom. And in the present case, this boson is known as a pion. And Yukawa developed this theory as the theory of the strong nuclear force. For a variety of reasons, it turns out that this is not the complete theory of nuclear forces. But when studying nuclei at low energies, this Yukawa theory, the pion theory that we're discussing, is a very good approximation. Okay? So you can view the theory that we're going to develop today either as a toy model of quantum electrodynamics, where I discard the spin of the photon and treat it as a scalar, or you could view it as a theory of the strong nuclear force, where the fermions are the nuclei in the center of an atom. Or you could actually view this as a sector of the Standard Model, where the boson now is the boson, the scalar field of the Standard Model, that is to say the Higgs, and the Dirac fermions are any of the matter fields, quarks, electrons, and so forth, present in the Standard Model of particle physics. Okay. So the Yukawa theory is an important theory. It's a slightly simpler theory than the theory of quantum electrodynamics. And it's a theory where we'll be able to get some practice with manipulating spinners in Feynman diagrams before we move on, hopefully next class, to the full theory of quantum electrodynamics. So the action of the theory is just the usual action of a real scalar field. So I'll give the scalar field a mass that I'll call capital M. So its kinetic term I've written there. I've integrated it by parts to make it look a bit more symmetric. We have the Dirac fermion field with a mass that I'll call little m. And then we have a coupling, which I'll call Y, between the scalar field and the fermion fields. And remember, these Dirac fermions are charged, so there's only one possible kind of interaction I can write down, which is an interaction of the form psi bar psi. And I've called the coupling constant Y because this is typically known as Yukawa coupling. And for example, in the standard model of particle physics, if phi were the Higgs, then there would be a whole bunch of Yukawa couplings of this form, coupling the Higgs field to all of the various different particles of the standard model, the different fermions of the standard model. So we could then go ahead and apply our machinery, our Feynman diagram machinery, in order to compute the various Feynman rules for the theory. Maybe just so that we all remember how this goes, I'll sketch this for you very briefly. Although in general in this class, we want to move to a point where if I hand you a Lagrangian, you can just go ahead and write down the Feynman rules without going through any intermediate steps of manipulating, generating functionals and path integrals and so forth. But just to remind you, and so that we all remember how this goes, let's just remind ourselves of how the path integral quantization of Yukawa theory would proceed. So we must introduce this generating function that I've called z, which is a function of three sources, a source j, which will couple to the scalar field, and sources eta and eta bar, which are now anti-commuting variables, they're Grassmann variables, rather than regular commuting variables. And they also have some spinor indices, 4 of them, which I have suppressed here. So these are spinors. And they have a spinor index because they have to act as sources for a spinor field. So that, for example, the coupling terms that couple these to the spinor fields that they source would look like this. So you would have an eta bar psi plus psi bar eta. And then, in the absence of the Yukawa coupling term y, we know exactly how to do this path integral. It's just a Gaussian path integral. We did the scalar version of this integral a few weeks ago, and we did the Grassmann version where we integrated over psi and psi bar last class. And what would the if y were equal to 0, if there was no coupling term, then the answer would just, well, you would have a d4x, a d4y, and you would just be doing a Gaussian integral with this source term here. And so you would get one term that looks like j of x, delta of x minus y, j of y, where delta is the scalar propagator. And then you would get a second term involving the spinors, so you would get an eta bar s of x minus y eta, where these are evaluated at x and y, where s is the propagator of the Dirac field. So this is just, so formally speaking, you could view this z free as the result of a Gaussian integral. And remember, when you do a Gaussian integral of e, integral dx of e to the minus, say, bx squared plus jx, what do you get? You get j b inverse times j, which is exactly what we have here, where the propagator delta is the inverse of this kinetic term here in the Lagrangian, just as this spinor propagator is the inverse of this kinetic operator for the Dirac field. In order to incorporate the effect of this interaction, what we do is we do the usual trick where we view the insertion of the psi bar, psi, and phi fields as the insertion of some variational derivative. So you get an e to the iy times an integral d4x of d by d j of x d by d eta of x and a d by d eta bar of x, all acting on the free generating function. And here I've written out explicitly the spinor index. It's something that we don't usually like to do, but I've written out explicitly the spinor index, which I've called alpha here. And I'm contracting those two spinor indices together because the spinor indices of psi bar and psi here are contracted together. And then, from this generating function, z, if we wanted to compute one of the observables of the theory, say a correlation function, that's just found by taking derivatives of this generating function. So, for example, if you wanted to compute a correlation function of a bunch of phi's with a bunch of psi's and a bunch of psi bars, then you would just need to take a bunch of derivatives with respect to j, and you would need a factor of I there because you have this factor of I here. And you would need to take a derivative with respect to j for each phi. So we could put a phi of x, or you would take a d by dj of x. And then you would need to take a derivative with respect to psi bar to pull down a factor of eta bar to pull down a factor of psi. So if we wanted to insert that at point y, we would pull down we would insert a factor of d by d eta bar. And then for each factor of psi bar, we would need to take a derivative with respect to eta. Okay. Say inserted at point z. And all of this would act on your generating function. And then after taking those variational derivatives, you would set all the j's and etas equal to 0. And there's one subtlety that we pointed out last time, which is that you would actually need a minus I rather than an I here. The reason being that you need to commute this d by d eta bar through this psi bar here. So you get a relative minus sign between those terms. And maybe, do I need minus i's in front of each one of those instead of i's? Is that why you're raising your hand? I probably need minus i's. The important thing is the relative minus sign that I wanted to emphasize here. We also need to be careful about the indices. So for example, you would have an index, say alpha 1 here, so you would need to have a d by d eta alpha 1. And say if you had a alpha 2 here, you would need a d by d eta alpha 2. Okay. So is anything unclear about this? I mean, we've gone through this sort of derivation a few times in this class. I think this is the last time I want to try and go through this formal derivation of the Feynman rules. In the future, I'm probably just going to write down actions and just write down the Feynman rules. But so let me pause here and see if there are any questions. Yes, in the back.
When contracting two spinners together, how do you do that?
When contracting two spinners together, what we really mean is you're just multiplying them together. Remember that you think of psi as a 4-component column vector. Psi bar is almost the 4-component row vector, except you had to multiply by a gamma 0, which is why we called it psi bar instead of psi dagger. So when I say contract indices together, I mean you take the dot product in the sense of you multiply a row vector times a column vector, right? So that's just the usual statement. So remember that in the Einstein summation notation, contracting two indices together is matrix multiplication.
So there's just no equivalent of a metric for spinners.
There's no, or if you want to say it that way, the metric is the flat metric. Good. Okay, next question?
Just the bars in this last equation, there are like two sides. One is
Oh, I'm sorry. So there's not supposed to be a bar there. Sorry about that. Good. Thank you. As usual, typos are introduced to make sure that you're paying attention. Good. Any other questions? Okay. So I just hope that is the derivation, are all the logical steps that I'm following here clear to everyone? You know, this is something that hopefully we've gone through a few times, and so hopefully it's clear. If it's not, please interrupt me and ask questions. And then the point is that the expansion of these two exponentials leads to a Feynman diagram expansion, just as in the scalar field case. So remember, in the scalar field case, we expanded out this exponential, and we expanded out this exponential in powers of the coupling constant y. And each time you did that, you would introduce a new vertex in the Feynman diagram. And we would expand out this exponential here. Really, I guess we would have two different exponentials if you view the exponential of the sum as a product of exponentials. And each term in that exponential would give you another factor of a propagator, which would be a line connecting two of these vertices. And then this leads to Feynman diagrams that can be written either in position space or in momentum space. Mostly in this class we'll be focused on momentum space Feynman rules because they're so much simpler. But again, because this is the last time I think I'm going to go through this in complete gory detail, let me just work out the position space Feynman rules. So the way that we write down the position space Feynman rules is we introduce a scalar source, which we denote by a black dot, as well as a fermion source, which I guess we could also indicate by a black dot. But you know that it's a fermion because it's connected to a fermion line instead of a scalar line. So here I'm denoting with a dotted line the scalar fields, and with a solid line the fermion fields. So for example, each one of these scalars would be a scalar propagator. Delta, and each one of these fermion sources would be given by a solid line, and this would bring down a factor of the fermion propagator, which I called S. Now, a couple comments are in order. So the first comment is that we have a charge flow arrow, also sometimes called a particle flow arrow, to signify which direction charge flows in a diagram or in some sort of process. So, for example, remember that the psi particles have positive charge, and the psi operator has a positive charge because it either creates a particle with positive charge or removes an antiparticle with negative charge. And similarly, the psi bar operator has negative charge. So here, for example, if you wanted to, you would need to really, if you wanted to be careful, introduce two fermion sources. So there would be another fermion source that looks like this. So this here would be a source for a psi particle because it creates charge, and so charge flows out of it. And this would be a source for a psi bar, and this would be your scalar source. And of course, these fermions also have indices. So we would have to attach an index, say, to each one of these legs. And then, although we don't like to indicate it explicitly, the fermion propagator is really a 4x4 matrix. You know, S is a 4x4 matrix. And we could, if we wanted to denote those indices explicitly, we would attach little fermion indices to the endpoints of one of the fermion propagators. And finally, because we have an interacting theory, we have an interaction vertex where a scalar can turn into a fermion-antifermion pair, say an electron-positron pair, if we were studying electrodynamics. And the charge flow arrows in this diagram have to reflect the fact that charge is conserved in this interaction. So here you have one charge flow arrow flowing into the vertex and one flowing out of the vertex. So this is the interaction. And in a position, so this, which would be equal to I times Y. And in a position space Feynman diagram, each interaction vertex as well as source has a position labeling the endpoints, or labeling the vertices. So there's a position for each interaction vertex and a position for each of the sources. And then the full Feynman diagram is computed by integrating over all possible locations of the interaction vertex, okay? Just as in the scalar theory. So, for example, let's imagine some of the terms that would contribute to the full generating function. So if we were, for example, interested in computing a correlation function between phi, psi, and psi bar, so this would be describe, say, the amplitude for some psi particle to decay into a psi and a psi bar, then you would have a term like this in your Feynman diagram, where you have one scalar source and two fermion sources. Or if you wanted to describe two scalar fields colliding together and annihilating and forming a fermion-antifermion pair, then you would have to consider a term in your generating function that looks like this. Or if you wanted to consider, say, a 4 Fermi interaction, then you would have to consider a term in the generating function that looks like this. Oops, sorry. That is one term that would contribute to the 4 Fermi interaction. It's actually not the simplest term. The simplest term, of course, would involve only the exchange of one of these pions. And indeed, in the Yukawa theory, if you imagine this as a theory of the strong nuclear force, the force carriers of the strong nuclear force are very massive. They're very hard to observe. But the nucleons are very easy to observe. They're just protons and neutrons. And so the way that Yukawa would observe this Yukawa theory of the strong nuclear force is he would imagine, for example, studying the interaction between two of these nucleons and modeling it via the exchange of one of these pions. Okay? And in fact, a little later on in this class, we'll understand exactly how this Yukawa's theory can describe the interactions between nuclei precisely using a diagram of this sort. And of course, there'll be many other terms, an infinite number of other terms in the generating function that include more sources, that include more complicated diagrams with loops, and so on and so forth. Okay. Now, it's important to note that the spinor propagators are matrices. And they must be multiplied in an order which reflects how the fermion lines are arranged in a diagram. So, in particular, what you need to keep in mind is that fermion indices in these diagrams must be contracted, that is to say, multiplied together, along the lines of particle flow. So what do we mean by that explicitly? Well, so let's just consider this diagram right here. Okay. So let's consider this as a contribution to, say, a psi-psi, phi-phi 4-point function. Here, and let me give myself a little bit more room. So let's say we have psi of x, psi bar of y, phi of z1, and phi of z2. So how would we go ahead and read that off from this Feynman diagram? Well, so here the fermions are inserted at x and y. Psi is inserted at x because that's a source for charge. The phi is inserted at y because it's a sink for charge, so the arrow flows into it. And here the two scalars are inserted at z1 and z2. And let's say that the interactions happen at locations w1 and w2. Then in order to compute the contribution to this correlation function, coming from that Feynman diagram, what do we need to do? Well, we get two factors of the coupling constant. So we have 2 powers of I times y. We need to integrate over the locations of the interaction vertices. And then we get 3 powers of the propagator. Okay? So you get a fermion propagator between x and w2, w1, coming from this line here. You get a fermion propagator from w1 to w2, coming from here. And you get a fermion propagator from w2 to y, coming from this final interaction, from the final propagator. And you also get 2 scalar propagators. You get a delta from z1 to w1, along with a delta from z2 to w2. The important thing to keep in mind here is that these propagators are matrices. The S's are 4x4 matrices. So I had to be very careful about the order that I wrote down this matrix product. In particular, if I wanted to be completely careful, I should remind myself that psi here has an index, psi bar also has an index, and so really this is an S. If you wanted to write out all the matrices explicitly, you could write it as an S alpha gamma, S gamma delta, S delta beta, where as usual repeated indices are summed over. And so you multiply those 3 matrices together to get another matrix, and that matrix is the 2 indices of that matrix are the indices on these 2 spinors. So is that clear? I want to make sure that this is completely clear to everyone. So the rule that you need to keep in mind is that fermion indices are contracted along the lines of charge flow. Yes? Yes, so in that case, you just need to be very careful. So that's the next case that we're going to do. So I'm going to compute that diagram for you in a minute. I'll actually do it, I think I might do it in momentum space rather than position space, but you need to be careful. So for example, okay, let's just go ahead and do it. Okay, so let's just go ahead and do it. So for example, if you wanted to compute, say, psi bar, psi bar, okay, which would be the thing that's computed by this Feynman diagram here. Sorry, before I do that computation, were there any questions on the earlier computation? Yeah.
Just, I guess I'm curious about what if you had a loop that had the arrows going in a circle?
Good. Absolutely. So what that means is that, so this is something that we actually mentioned at the end of class last time. If you have arrows that connect up in a loop, that means that all of the indices are contracted together. So for example, let's say that you had something like this. So let's say you were computing the scalar field 2-point function. This would be proportional to an IY squared. You would have to integrate dw1, dw2, where these are, so let's say that's at x, that's at y, this is w1, w2. You would have to integrate over w1, w2, and you would get a propagator of, say, w1 to w2, and another propagator w1 to w2. And, well, first of all, you have the usual, you have to contract both of those indices together. So if you think of S as a 4x4 matrix, S times S, and then you contract the final two indices together, that's something that you all know the name of. If you think about S as 4x4 matrices, when you multiply them together, you're contracting one of the indices together. And when you contract the other indices together, what are you doing? You're taking the trace, right? So this is the trace of S times S. And then, of course, you would have two other propagators. You would have a propagator from X to W1 and from W2 to Y. So that's an important point. Fermion loops, for every fermion loop, you have to trace over the fermion index, And in fact, that's not just true for fermion indices. If we were considering, for example, scalar QED, as we did last week, and you wanted to compute a correction to the propagator from a photon loop, then you need to sum over the, you would have something like that. I guess we would. So in scalar QED, you would have something like that. And then you would have to trace over that internal propagator. And in fact, that's a diagram that we will actually end up computing and studying in some detail in quantum electrodynamics. Good. Excellent. Okay, any other questions? Yes.
With the, sorry, I can't really read the writing. But
Sorry.
The S matrices that are multiplied together, are there any free indices left in that? Or are they all contracted together? Like
Well, so in this diagram,
I mean in the one above.
in the one above, so it's supposed to be matrix multiplication, so the second index of one is contracted with the first index of the next. So the second index here is contracted with the first index here. Second index here is contracted with the first index here. And you get a free index here and a free index there. And that's supposed to, if you stare at this diagram, we could also be attaching indices to each one of these things. So remember, you have an index here, and you have indices for each propagator. And so, this diagram is getting a little sort of too full of notation. But really, you have indices. This propagator is instructing you how the indices should be arranged. Usually we don't like writing out the indices explicitly because then your diagrams get so complicated you can't read anything. But if I were to write out the indices, well, I would have, say, what did I call it, a beta index there. Here, this propagator has a beta index over here, and what did I call it, a delta index here. Is that what I called it? Yeah, so I guess this propagator has a beta index and a delta index. This propagator has a delta index and a gamma index, and this propagator has a gamma index and an alpha index. Right. Hopefully that makes things more clear rather than less. There's always the danger that you can keep explaining things, and once you explain it too much, the curve inverts, and the amount of understanding starts decreasing instead of increasing. Hopefully I haven't achieved that point yet. Maybe I'm way past it. Any other questions? Let's do another example, just to make everything totally clear. So let's imagine we're computing, say, what is the diagram that I wrote down above? Let's say we're looking at this diagram, which contributes to a fermion 4-point function. So we have, let's say that we have, so you got a psi here, a psi bar there, a psi here, and a psi bar there. Then this contributes to the fermion 4-point function. And what is its contribution? Well, you get a psi, psi bar, psi, psi bar. So let's say that we want to compute this guy. Well, in order to keep all of our indices straight, I should really decide on what the indices are for these various spinors. So I'll call that a psi alpha, psi bar beta, psi gamma, psi bar delta. Then what will this be? Well, you'll get 2 copies of the coupling constant squared, Iy squared. Then you have to integrate over the locations of the vertices. So I'll put them at W1 and W2. So you get an integral d4 W1 and an integral d4 W2. And so what do you get? Well, first you get the propagator from, so let's say that these are at points x1 and x2, x3 and x4. So you'll get a propagator from x1 to w1 and a propagator from w1 to x2. So those are 4x4 matrices. You multiply them together, you get another 4x4 matrices. And its indices, those 4x4 matrices, that 4x4 matrices has indices alpha, beta, okay, which map up with these guys here. And then you'll get an S of x3 minus w2 times an S of w2 minus x4. And those are 2 4x4 matrices that you multiply them together. You get another 4x4 matrix whose indices are gamma delta. And then you get a scalar propagator, which is a delta of w1 minus w2. Okay, any questions on that? So that's how the various contributions of this diagram to this 4-point function would be matched up. Now, there's one interesting point that I want to make, which is that there's another diagram. So if you like, you could call this the T-channel diagram, where, well, because it looks like the T-channel diagram for 2 to 2 scattering that we studied earlier. But there's another contribution to this, which would be the U-channel diagram, where you just interchange these last 2 points. Okay. And the important point that we want to make is that whereas when you considered external scalars, you would just add the U-channel diagram, when you have external spinors, you actually have to subtract the U-channel diagram. So the U-channel diagram would be the one where, say, x2 and w1 are interchanged with x4 and w2. I guess you don't even really need to interchange w1 and w2. You could just undo that by a change of variables. But in any case, the point really is that you pick up a minus sign here because every time you permute initial or final states, when you have fermions, you'll pick up a minus sign. That's practically the definition of a fermion. So this is from permuting final states. And in general, if we permute final states, either external states, either initial or final states, you're going to, if you have an even permutation, then there's no sign change, so you just get a plus. Whereas if you have an odd permutation, an odd number of interchanges, then you'll pick up a minus sign. So in general, the rule, yeah, okay, question.
Yeah, my question is, so if I had started writing down the U-channel
Yes.
diagram and I wanted to write out what
Right.
the expression was, is there some way that
You would
minus
fix,
sign
yes,
becomes-
absolutely.
Yeah.
If you wanted to be super careful about it, how would you do it? Well, if you wanted to compute psi alpha, psi bar beta, psi gamma, psi bar delta, you would write down a d by d eta alpha, eta bar alpha, a d by d eta beta, a d by d eta bar gamma, and a d by d eta delta of this partition function. And you would have to just keep very careful track of the ordering of all of these guys. Usually, thankfully, the only thing you're ever interested in computing are probabilities rather than amplitudes. So overall signs of diagrams are usually not very important. Okay, that's actually a bit of a lie. Because, for example, in about 5 minutes, I'm going to make a big deal about the overall sign of this diagram. Okay, so sometimes you can get away without keeping track of this, but very often you don't actually care about the overall sign of the diagram. In this case, it actually turns out that the overall sign of this diagram is important. Why is it? Well, in momentum space, that's going to describe the scattering of two of these spinors off of one another. And the sign of that amplitude is the thing that tells you whether it's an attractive force or a repulsive force. Okay? So that's something that would be important if you want to try and understand physically how this Yukawa theory is a model of the strong nuclear force. So just as a hint, in the nuclear force, you want your nuclei to attract one another, not repel them. Good. Excellent. Any other questions on this? Before I go through that, though, I want to talk a little bit more about how we would understand these diagrams in momentum space rather than position space. Questions? So, to study the momentum space diagrams, to compute, for example, scattering amplitudes, if we wanted to go through the argument in detail, then what I would have to do is rederive the LSZ reduction formula for these fermions. But if I were to do so, the argument would go almost exactly as it did with the scalars. So I remind you that the LSZ reduction formula is the trick that we use to extract scattering amplitudes from correlation functions. So you start with the position space correlation functions, whose Feynman rules we've derived. Then you extract from those Feynman rules in momentum space for computing scattering amplitudes. And the basic lesson was that if you want to compute, say, 2-to-2 scattering, then you need to compute a 4-point function in position space. And the LSZ formula just basically tells you that you get to strip off the propagators associated with those external states. And you can trust me when I say that essentially the exact same thing happens when you do this with spinors, the only difference being that you need to keep track of the spinor index. And likewise, the same thing happens when you do this with photons, the only difference being that you now need to keep track of the index of the photon, the mu of the A mu, which will turn into some dependence on the polarization of these fermions or of these photons. So without any further ado, let me just go ahead and write down the momentum space Feynman rules for this Yukawa theory. Okay. The Feynman rules for quantum electrodynamics will just be one tiny modification of these. So in writing the Feynman rules, I'm going to again use the notation that incoming particles will be on the left of my Feynman diagram, and that outgoing particles will be on the right of my Feynman diagram. An arrow, so for an incoming particle, so what this means, for example, is that you would represent an incoming particle as something like that. So this would be an incoming, say, electron, if we were studying a theory of electrons and positrons, whereas an incoming positron would be denoted by an arrow by a leg that's coming in from the left as well, but now with the charge arrow reversed. Okay? This charge arrow just denotes the direction that charge is flowing, remember, not necessarily the direction that particles are moving. Similarly, we'll also use the notation that momentum flows from left to right in the diagram. Although, so certainly this is the most convenient thing to do for external legs. For particles for legs that are arranged vertically, we're going to have to, keep track of which direction the momentum flows explicitly. And generally, for loops, we will often use the notation where momentum flows in the direction of particle flow. So we're not going to be doing too many loop diagrams this semester, so this notation won't be too important for now. So without any further ado, we can go ahead and write down the Feynman rules. Okay. So the Feynman rules say that for each incoming electron, you need to include a vertex. You need to include some external leg to your Feynman diagram that looks like this, which will be labeled by, say, the momentum of that electron. And when you say that you have some incoming electron in some Feynman diagram process, you need to specify the polarization of that electron. So you need to specify some polarization, which we would call, which remember we called U of P. And here S is an index that labels the two possible different polarizations of an electron. So I've introduced an index S1 here that can be either 1 or 2, depending on whether we have a polarization 1 or polarization 2. And the point being that for every incoming electron with polarization 1, you need to introduce one of these polarization factors U. The reason for this is that I remind you that when we quantized the electromagnetic field, or when we quantized the Dirac field, the operator psi, well, when we quantized it in terms of raising and lowering operators, we had a factor of U for every raising operator, or, well, rather psi had a factor of U times A plus something that we called V times B dagger. And so if you want to describe a process where you have some incoming electron, then there's going to be a factor of the polarization of that electron in the Feynman diagram. Similarly, if you have an outgoing electron, then you need to include an outgoing leg on the right side of your Feynman diagram. So we could give it some momentum that we could call P1 prime. And just as the operator A that removed an electron was multiplied by U, the operator A dagger that created an electron, so we could let's call it S1 prime, was multiplied by U bar. There has to be some factor of U bar for every outgoing electron. Similarly, if we have an incoming positron, then you'll have an external leg like so, and the positron raising and lowering operators were multiplied by V's and V bars. And so if you go through the rules, you'll need a V bar here. So we could call that P1, its momentum. And here, and finally, if you have an outgoing positron, then that would be represented in a Feynman diagram by an external leg on the right with an arrow pointing to the left, and you'll get a factor of V associated with that. So I guess we called P1 prime, say, the momentum of that outgoing positron, and you'll get a VS1 prime of P1 prime. So those are the external leg factors that keep track of the polarizations of the incoming and outgoing electrons and positrons. What you really just need to remember is that you get a U for every electron and a V for every positron, and that you get a bar every time one of these the charge flow is leaving the Feynman diagram, and you get no bar every time the charge flow is pointing towards the interior of the Feynman diagram. You also, of course, have some incoming scalars. So an incoming scalar would be denoted with a line on the right. An outgoing scalar is denoted by a line on the left. And of course, these would be labeled by their momentum as well. And so if you're instructed, say, to compute a scattering process with some number of incoming or outgoing electrons, scalars, and positrons, the Feynman diagram rules say that we should join all of the external lines using interaction vertices, which are these trivalent interaction vertices. And we get a factor just as we get a factor of IY for each interaction vertex. And we have to join these in all ways that are consistent with charge conservation. So in particular, what this means is that all of the arrows have to line up. If you have an arrow going out of one interaction vertex, then that either needs to go into another interaction vertex or it needs to exit the diagram. Yes?
I'm getting confused, but wasn't our notation or our convention with the charge flow the opposite before? Like positive charge flow with positron?
Yeah, I'm sorry. No, you're completely right. Where usually, yeah, it's because somebody decided that an electron had negative charge. Okay, so whoever defined charge happens to have decided that electrons have negative charge instead of positive charge. So that means that sometimes, oh my, that means that sometimes, yeah, we're going to have to mix our metaphors a little bit. So usually, if I was talking about, say, the Yukawa theory of the nuclear force, you're probably right that I would say charge flow points in the direction of increasing charge. The arrows point in the direction of increasing charge. Typically in quantum electrodynamics, we call this particle flow instead of charge flow because we usually take it to point in the direction of negative charge flow instead of positive charge flow. It completely doesn't matter as long as you are consistent. Okay. Yeah. Good. Excellent question. Yeah. Good. And now let me just finish stating the Feynman rules. These are things that you already know. So each line in a Feynman diagram gets a momentum, and momentum is conserved at interaction points. And so what this means is that in a tree diagram, that is to say a diagram with no loops, all of the momenta will be determined by momentum conservation. In particular, in a tree diagram, when if you have no loops, then all of the momenta will be determined by the momenta of the external particles. But we integrate over the undetermined momenta in any diagram which has a loop. And the number of loops is the number of undetermined momenta. So each line in the diagram will get a propagator. Remember that external lines don't get propagators. Those are the things that are stripped off when we do the LSZ reduction formula. But the internal lines get propagators. And here we just need to write down the propagators in momentum space. So if capital M is the mass of our scalar field, then the propagator for a scalar field is I over k squared minus m squared. And the propagator for a spinor field is I over p slash minus m, where little m is the mass of the spinor field. And again, I remind you that p slash is a 4x4 matrix. So here, this propagator that I've written is really a 4x4 matrix acting on these spinor indices. And finally, we need to remember that fermion indices, spinor indices, contract along lines of charge flow. In particular, what that means is that we need to multiply spinor indices by starting with a U bar or a V bar and following the lines, following the little charge arrows until we get a U or a V bar. Sorry, a U or a V. So in particular, I want you to remember that scalar quantities are things of the form U bar times some matrix times U. Okay? And so if you want to get something scalar with no free spinor indices, you need to start with one of these spinor lines. You need to take one of these spinor lines, find a U bar, which will be one of the guys. You find a U bar or a V bar, you need to find one of these guys with the charge arrows pointing out of the diagram, and you need to follow those spinor indices until you end up with a U or a V. And finally, and this is the rule that we mentioned last time, you get a factor of -1 for each fermion loop. Not something that'll be so important this semester, but a very important fact that is, for example, responsible for the fact that quantum chromodynamics is asymptotically free rather than asymptotically strong, like quantum electrodynamics. So if this is all a lot to handle all at once, don't worry. We're going to spend the next couple of weeks sort of using these Feynman diagrams in every which possible way to compute quantities of interest in quantum electrodynamics. But let me just do a simple example for you right now, which is 2-to-2 scattering of spinors in Yukawa theory. So if you think of the Yukawa theory as a theory of the strong nuclear force, then this is the sort of experiment that you might use. This is the sort of interaction you might actually imagine studying if you wanted to understand the properties of this strong nuclear force. You might, for example, consider scattering two protons off of one another, and by observing the scattering process, try and understand the details of the nuclear force between two protons. Say the nuclear force that would bind two protons together in the nucleus of a helium atom. So let's consider then the scattering process. So I guess in the rules that I wrote down above, I call the particles electrons, okay, although they could just as well be protons. So how would you describe the scattering process? Well, let's say that the incoming particles have momentum P1 and P2, along with polarizations U1 and U2, and that the outcoming particles have momenta P1 prime and P2 prime, along with polarizations U1 prime and U2 prime. By momentum conservation, the scalar that we exchange will have a momentum which is P1 minus P1 prime, so this would be one contribution to the diagram, to this process. And then there'll be a second contribution from a process where the electron 1, well, because these are identical particles, where the P2 prime and P1 prime are interchanged. And there's a relative minus sign coming from the exchange of these external particles. If you like, you should really call that another one of your Feynman rules. I'll call it point 2 here. So you get a -1 for each exchange of external legs. Now you might say, -1 compared to what? How do you choose some fiducial ordering? Well, you just choose an ordering, and you only ever care about the relative minus sign. So what is the value of this sum of diagrams? Well, let's look at that first diagram here. Well, you get two factors of the Yukawa coupling. Here, I guess I should have drawn my arrows there. You get two factors of the Yukawa coupling. Then you get, for this diagram here, you get a U1 bar prime U1. So that's a scalar. It comes from contracting fermion indices along this top line here. And you get a U2 bar prime U2 from contracting indices along that bottom line. And then you have the scalar propagator, which gives you I over the momentum P1 minus P1 prime quantity squared minus m squared. So that's what we call T minus m squared, where T was that Mandelstam variable. And then from the second diagram, you get a U2 bar prime U1 times U1 bar prime U2 over the variable which is now, so what is this momentum here? This momentum here is now P1 minus P2 prime, which is what we would call U in terms of those Mandelstam variables. And that's it. That's your Feynman diagram. So, are there any questions on how I went about computing that? Are those rules more or less clear? You know, the rules, when you state them abstractly at those 12 different points, it sounds kind of abstract, but once you write down a Feynman diagram, you just remember the rule that you have to multiply fermion, that you're getting a scalar at the end of the day, and that you're multiplying all these fermions together, contracting them along these charge lines. It's actually really not that hard. I did want to go through and work out the Yukawa case first today before moving on to QED, because it gets a little more complicated when we do QED. Good. Any questions? Yes. Yes. Yeah. So it usually we write the black dots in position space, but not in momentum space, right?
But then maybe can you scroll up?
Yes.
So you associate it with something with
Oh, this black dot. Sorry, these are not supposed to be black dots. Sorry. Okay. Those are not supposed to be black dots. That's supposed to be the rest of the Feynman diagram. Sorry. I hope that was more or less clear. So the idea is that for every incoming electron, you have some incoming leg coming from the right. So here I've drawn the leg. Here I've drawn the rest of the Feynman diagram. Okay, that blob is supposed to be the rest of the Feynman diagram. Okay, I hope that's more or less clear. And likewise, for an outgoing state, this blob here is the rest of the Feynman diagram. It's spitting out some electron going to the right. Good. Good. Sorry, I hope that's clear. Good. Okay. Good. Okay. Now, let's imagine that we were actually doing this experiment, where we have, say, two protons and we're banging them off of each other, and using that to try and determine the nature of the force, the nuclear force by which these protons interact with one another. Well, in principle, we should be able to determine the nature of the force by studying this scattering amplitude. In particular, if you imagine scattering two protons off of each other and studying that scattering amplitude as a function of energy, that should tell you all of the details about how these protons are interacting with one another. You could imagine, for example, an analogy with Rutherford scattering, or an analogy with the scattering of charged particles off of each other. So in electromagnetism, you could say, take two protons together, and you could study their scattering off of each other in classical electromagnetism. Okay, that's just some sort of straightforward. It's complicated, but it's a completely straightforward problem in classical electromagnetism. And then by studying that scattering process, you could learn Coulomb's law. And so the claim is that this expression that we've written here contains the analog of Coulomb's law for the nuclear force. In particular, we should be able to read off from this expression the analog of Coulomb's law for Yukawa's theory of the strong nuclear force. So let's go ahead and do that. So to make life simple, let's imagine that instead of scattering indistinguishable identical particles off of one another, let's imagine that we were studying the scattering of distinguishable particles rather than identical particles. What does this mean? All this means is that you imagine, say, attaching little labels to these particles and then studying their scattering off of one another, and only studying, say, the first process. So this is, by attaching labels to these particles, you could tell the difference between that first diagram and the second diagram. So if the particles are distinguishable, then we could choose just to focus on the first diagram. So then the scattering amplitude, so it would just come from that first diagram. So let me just write it down for you again, which is I times IY squared times U bar 1 prime U1 u2 bar prime u2 over t squared minus m squared. So that's p1 minus p1 prime minus m squared. Okay. So here this is a p1, and that's p1 prime. Good. So what I want to do is I want to compare this with our usual sort of electromagnetism intuition. Yes, question.
Does that need to be squared in the denominator?
Squared. Thank you. Good. Okay. And so in order to do this, I want you to consider the non-relativistic limit. In the non-relativistic limit, this should boil down to some quantum mechanics scattering amplitude. And so how does the non-relativistic limit work? So in the non-relativistic limit, one of these four momenta, say p, what is it? Well, it's the energy momentum 4 vector, which at leading order has a zero component, which is just mc squared, the rest energy of the particle. Its other three components are the momentum 3 vector, and there are relativistic corrections that will be neglected. Similarly, in the non-relativistic limit, that means that you're essentially working in the rest frame of these spinors. And in the rest frame, we derived an expression for these spinors. Remember, these are 4-component spinors. But in the rest frame, you can just write them as two-component spinors on top of one another. So here, zeta s is a basis of the space of 2-component spinors, and these are the usual spinors of quantum mechanics. These are the usual 2-component spinors that you would use to describe a spin 1/2 particle in quantum mechanics. So what does that mean? That means, for example, that that means, for example, that let's call the initial spin here u1s and u1s prime. So here we're imagining a particle with a momentum, incoming particle with a momentum p1 and spin and polarization s. And the final particle has momentum p1 prime and polarization s prime, where s is just a label 1 or 2 that tells you the 2 different polarization states. Then we need to write down u1 bar prime, I guess s prime, times u1s, and that is just 2m times zeta s prime dagger zeta s. And remember, we choose a basis of 2-component spinors so that they're orthogonal. So this is just 2m delta s s prime. So what we're seeing here is something that is not fancy at all. It's saying that if you send in a particle, your p1 particle, your particle 1 has spin s, then the outgoing particle has the same spin. Okay? That's all we're saying. So for example, the 2-component spinors zeta s, they could describe, say, spin up and spin down relative to, say, the z direction. Then this scattering this tells us that if you send in a particle with spin up, it'll have spin up afterwards. If you send in a particle with spin down, it'll have spin down afterwards. That's what that delta s s prime means. Another way of thinking about that is that they're interchanging a scalar particle. Scalars don't carry spin, so there's no way that the 2 particles that were scattering off of each other could exchange spin with one another. So that you send in one particle with spin s, it'll have the same spin when it comes out. In quantum electrodynamics, the situation is going to be more complicated because they're exchanging a particle with spin. The photon has spin 1. So similarly, if we call the particle down here, say P2, which has a spin U2, let's call it R, and this guy has P2 prime, U2 R prime, then the total scattering amplitude, putting all this together, you get an I, you get Y squared, you get delta S S prime, delta R R prime, and you get a divided by P minus P prime. So in the denominator, what do you get? You get P minus P prime squared plus M squared. Where does that factor come from? That's just because in the non-relativistic limit, P minus P prime squared, what is that? Well, you just use this formula here. So P minus P prime in its 0 component is just 0. And so that's just minus P vector minus P vector prime squared. Good. Okay. So let me make 2 comments about this formula. So the first comment, as I mentioned above, is that spin is conserved. When you exchange a scalar particle, there's no way for these 2 particles to exchange spin with one another. The second comment I'll make is that the answer is proportional to y squared. And you should think about this in analogy with electromagnetism. So we'll do the electromagnetic case next class. But in electromagnetism, the amplitude with which 2 particles can scatter off of one another is proportional to the charge of the first particle times the charge of the second particle. That's Coulomb's law. And so this is supposed to be proportional to the factor, it's supposed to remind you of the factor of the electric charge squared that you would get in electromagnetism. So this means that the parameter y that we wrote down is a little bit like the charge that these particles carry with respect to some new force, the nuclear force that's generated by these pions. And indeed, from this formula that we've written off here, you can read off the analog of Coulomb's law for the Yukawa theory. So in order to do this, I'm going to need to remind you of something that you hopefully learned in your class on non-relativistic quantum mechanics. So in non-relativistic quantum mechanics, if you want to study scattering of a particle from a potential, then the easiest way to do that is to use the Born approximation. And what is the Born approximation? That says that if you take a particle, an incoming particle with a momentum p1, and you throw it at some potential, so let's say that you have a hydrogen atom and you've got a proton that's sitting there with some electric charge, some Coulomb potential. You throw an electron at it, then it'll scatter off, and the scattering amplitude, the transition amplitude, the amplitude for it to scatter into some new state with momentum p1 prime is given by, well, there's a factor of the Fourier transform of the Coulomb potential, or the scattering potential. And then there's a momentum conserving or an energy conserving delta function. Where here, what is this? This is the Fourier transform of the potential. So what that means is that by starting with our scattering amplitude and taking a non-relativistic limit, using the Born approximation, you can see what the potential is of this Yukawa theory. In particular, just comparing it with this formula here, we see that in momentum space, the potential is minus y squared over q squared plus m squared. Now, I'm out of time, so I won't compute the Fourier transform for you explicitly. Ooh, maybe I'll have you do it on a problem set. Okay, that's a good idea. So, the Fourier transform of this, or maybe I'll do it explicitly when I do it in QED. We'll see. So first of all, because this is a function only of the absolute value of q squared, that means that your potential is rotationally invariant. So it's a function only of radius. Moreover, it is proportional to minus y squared. And then there's some function of radius that appears. And the function that you get when you do the Fourier transform is 1 over r times e to the minus mr. So this is a potential. So the first thing that I want to notice is that if you set m equals to 0 here, this would be the usual Coulomb potential. That's practically dimensional analysis. It's just the statement that if you did, let's just do that exercise quickly. If you integrated d3q e to the I q dot x of 1 over q squared, then that is something that scales just dimensionally like q, and q has dimensions of 1 over x, so it scales like 1 over r. So you know that when m is equal to 0, it has to have a 1 over r here. The only question, so that is Coulomb's law. That's the Coulomb potential. Now the question is, what effect did the mass of the scalar field have? Well, it turns out if you do the calculation, the mass of the scalar field has the effect of introducing an exponential cutoff to this Coulomb type interaction. So this is known as the Yukawa potential. It's the analog of the Coulomb potential. But whereas the Coulomb potential is the potential that arises when particles interact through the exchange of a massless photon, the Yukawa potential is the potential that arises when particles interact through the exchange of a massive scalar particle. And the mass of the particle determines the scale of this exponential cutoff. And the reason why Yukawa likes this as a theory of the nuclear force and why it's actually such a successful theory of the nuclear force is that nuclear forces are very, very strong at short distances, but they fall off at large distances. And in particular, nuclear forces, observationally, tend to fall off rapidly at distances that are much greater than about a femtometer, so about 10 to the minus 15 meters. Okay? Sort of the size of a typical atomic nucleus. You know, I looked up, so for example, I think the radius of the nucleus of a helium atom, which has 2 protons, is about 10 to the minus 15 meters, 2 times 10 to the 15 meters, something like that. 10 to the minus 15 meters. Life would be very different if it was 10 to the 15. And so from that, you can, if you want to describe the interaction between nuclei using this Yukawa theory, where the nuclei interact via the exchange of a scalar particle, using that distance scale, you can immediately determine the mass of the particle. And the mass, if you just go ahead and plug in a femtometer, is going to be around 200 MeV. So several thousand times more massive than things like protons, neutrons, and so forth. Several hundred times more massive. And indeed, you can go to the particle data book and look up the mass of the pion. And it's close to that. It's about 140 MeV, something like that. And so, in fact, at low energies, this is a pretty good model for the strong nuclear force. So this is, I think, one of the first times in this class that we're using quantum field theory to model a real particle physics force that we haven't been able to do so before. Now, the actual nuclear force, it turns out, is only described by the Yukawa theory at relatively long distances. If you start banging these protons into each other at sufficiently high energy, I was imagining an experiment here where we were banging protons into each other at high energy and using that to study the nuclear force. Well, it turns out that if you bang them together at sufficiently high energy, they actually break apart into more elementary particles. And so this Yukawa theory is only what's known as an effective theory. That is to say, it's a theory that works well for some finite range of energies. It works very well at low energies, but things go wrong with it at very high energies, and you need to go to the theory of quarks and gluons. I will make one very important point. Sorry for going over time, but the final point I want to make is that the Yukawa theory is attractive. And one of the important points is that here we've studied the scattering of, say, a proton and a proton, or an electron and an electron, using this Yukawa theory. You could also do the analogous computation for an electron and a positron. And if you were studying Coulomb interactions, you would find that electron-positron is attractive, and other way around. Yes, no, electron-electron is repulsive, and electron-positron is attractive. However, in the scalar theory, in this Yukawa theory, interactions are always attractive. Okay? And this is a qualitative difference between a theory where forces are governed by the exchange of scalar particles as opposed to the exchange of vector particles. So next class, we're going to do the analogous computation in QED. And we'll hopefully, although I'm never very good with the signs, but we'll hopefully find that like charges repel and opposite charges attract in QED. But if you go through the calculation in Yukawa theory, what you find is that no matter what sort of charges you give things, they always like to attract. Now, can anyone think of any other theory which has that property? Gravity, yes. So the thing that you should keep in mind is that theories quantum field theories with even spin particles, with integer spin particles, describe forces, and with odd spin particles, they describe matter. And the rule that you keep in mind is that particles with spin 0, 2, 4, and so forth describe forces that are always attractive. So gravity, the Yukawa theory, things like that. But for theories of force carriers with spin 1, 3, 5, and so forth will describe interactions which are either attractive or repulsive, depending on whether you're studying the interactions of particles or antiparticles. Good. Okay, sorry for going over time a little bit, but it's a sufficiently important computation I wanted to spend some time on it. Great. See you next class.